Hello, good afternoon. My name is Fabiola Castañeda Garcia. I am a PhD student in materials science and engineering at the University of Guadalajara. I am pleased to present my thesis entitled Waste Fishing Nets Sugarcane Fiber Composites, Processability Window and Mechanical Properties. Poster. The disposal of waste fishing nets has become an environmental concern due to their slow degradation and impact on marine life. Transforming these polymer wastes into new materials offers a sustainable approach aligned with circular economy principles. Sugarcane fibers, an abundant lignocellulosic byproduct, can serve as an effective reinforcement in polymer matrices, enhancing mechanical performance. This research aims to characterize fishing net polymers using FDR, DSC, and SEM to understand their physical and chemical properties. Composites will be produced by heat pressing these polymers with sugarcane fibers, and their tensile strength will be evaluated according to ASTM D638. The study seeks to define a processability window and correlate processing conditions with the mechanical behavior of the resulting composites. Beginning of the Anthropogenic era marks the beginning of significant human influence on the environment. 1868 Alexander Parkes invents Parksin. John W. Hyatt improves it, calls it celluloid, and uses it to make billiard balls. 1909 Leo Hendrik Baekeland, a Belgian-American chemist, creates and patents Bakelite, the first synthetic plastic. 1950s plastics replace traditional packaging. Production reaches 2 million tons. Environmental problems due to plastic waste are already beginning. 1960 first record of plastic waste in seabirds. 1980 plastic production increases and diversifies, becoming one of the world's leading industries. 2000 anti-plastic initiatives emerge, such as campaigns and organizations to reduce its use. 2025 present. The goal is to determine the physical and chemical characteristics of plastics and microplastics to better understand their environmental and health impact. Objectives. 1. Characterize polymer waste from fishing nets using FDR, DSC, SEM to determine their physical and chemical characteristics. 2. Obtain polymer/lignocellulosic fiber composites through heat pressing. 3. Characterize the mechanical strength of the composites using tensile testing according to ASTM D638. Materials and methods. 1. The experiments were conducted in the polymers laboratory at the University of Guadalajara. The nylon and sugarcane fibers were then oven-baked at 70 degrees Celsius for 24 hours. 2. The materials were then transferred to a hydraulic press. This machine processes the materials and molds them under pressure and temperature. The dry material is placed in this mold to give them a specific shape, rectangular plates. 3 and 4 plate production. The formed plates, some with visible plant fibers, are shown after demolding. 5 specimen punching. The plates were cut into standardized specimens, bone-shaped, for mechanical tensile testing. 6 characterization. A mechanical tensile test was performed using clamps according to ASTM D638, along with FDR and DSC analysis. FDR results of nylon. The slide shows 2 FDR, Fourier transform infrared spectroscopy, spectra of nylon 6. Top, green spectrum. Corresponds to the nylon 6 material used experimentally in your project. Several absorption bands are observed, with assignments in the characteristic regions. N, H, NH. Stretching signals appear between 3300 to 3200 cm superscript 1. Aliphatic C, H. Stretching modes are distinguished between 2930 to 2850 cm superscript 1. Aliphatic C, H. Stretching modes are distinguished between 1630 to 1530 cm superscript 1. Bands corresponding to amide I, C equals O stretching, and amide 2, N, H bending coupled with C, N stretching, characteristic of the peptide bond present in polyamides, are visible. The region between 1200 to 600 cm superscript 1 presents several signals associated with C, N, and C vibrations, typical of the polyamide backbone. Bottom, black spectrum. This is the reference spectrum reported in the literature for nylon 6. It presents the same main bands. 3298 cm superscript 1, N, H stretching. 2934 cm superscript 1, C, H stretching. 1636 cm superscript 1, amide I, C equals O stretching. 1535 cm superscript 1, amide 2, N, H bending plus C, N stretching. Microscope scientific comparison. The experimental spectrum above and the literature spectrum below show agreement in the characteristic bands of the amide and methylene functionalities, confirming that the material studied is indeed nylon 6. Small variations in peak intensity and shift may be due to experimental factors such as processing conditions, pressure, temperature, polymer crystallinity, residual moisture or impurities. Instrumental resolution. The DSC analysis results show the material is in a glassy, rigid, and brittle state. Above 195 degrees Celsius, it enters a rubbery state, greater chain mobility, flexible. The peak around 227 to 240 degrees Celsius corresponds to crystalline melting, TM, not TG. The TG point on the graph is 195 degrees C, T equals 194.87 degrees Celsius, and is key because it indicates the minimum temperature at which the polymer begins to become processable and molecularly mobile. The graph shows the stress-strain curves obtained from tensile tests for polyamide, PA, with the addition of 3% and 5% by weight of agave fiber. Each color corresponds to a different specimen as an experimental replicate, allowing for evaluation of the dispersion of results and the reproducibility of the reinforcement. Behavior with 5% agave fiber. The maximum stress reached is observed to be between 40 to 50 MPa. The strain at break is around 20 to 23%, indicating that the material retains some ductility despite the reinforcement. The three replicates show a similar trend, suggesting a relatively homogeneous distribution of fiber in the polymer matrix. The intermediate curves suggest localized yielding or the appearance of progressive damage mechanisms, microcracking, matrix fiber debonding. The 5% graph shows that the fiber improves initial stiffness, but introduces heterogeneities that limit maximum strength and maintain more brittle behavior. Consistency between repetitions indicates good reproducibility. Behavior with 3% agave fiber, bottom graph. There is a more marked dispersion. In the orange repetition, a strain of almost equals 75 MPa was observed with high strain, is almost equal to 25%, while the other two, blue and gray, are in the 30 to 40 MPa range and fail prematurely, 15–18% strain. This variability may be associated with inhomogeneous fiber distribution, the presence of agglomerates, or differences in the interfaciality between the matrix and reinforcement. The higher stress case suggests that, when the fiber is properly dispersed and oriented, it can transfer load more efficiently, significantly increasing strength. Therefore, it can be concluded that at low concentrations, 3%, the reinforcement is more sensitive to fiber distribution and orientation. Results with high potential performance are obtained, but with lower reproducibility, indicating the need to optimize processing. 1. The present micrographs show the general morphology of the fracture, low magnification 22x, 200x. Lower magnification images show a heterogeneous fracture surface, where the polyamide matrix exhibits a radial crack propagation pattern characteristic of a brittle fracture mechanism. At the same time, partially adhered fibers are observed, as well as cavities resulting from the detachment of reinforcements, which constitute direct evidence of interfacial phenomena. The lack of uniform adhesion suggests limited chemical compatibility between the polyamide matrix and the lignocellulosic fiber, attributable to differential polarity and the presence of hemicelluloses, lignin, and surface waxes in the plant fiber. 2. Internal fiber structure, intermediate and high magnifications, 200x, 300x. Higher-resolution micrographs reveal the typical cellular morphology of natural fibers: elongated lumens, multilayered cell walls, and structures collapsed during specimen preparation. These microstructural characteristics in sugarcane bagasse give the reinforcement a low specific weight, but simultaneously generate stress concentration sites and facilitate moisture absorption, factors that can compromise the composite's dimensional and mechanical stability. Likewise, torn fibers with relatively clean surfaces are identified, reinforcing the hypothesis of insufficient interfacial adhesion. However, in some sections, partial coverage of the fiber by the polyamide is evident, indicating a certain degree of mechanical anchoring. And this is the biography.